The broadcast is now starting. All attendees are in listen-only mode.
All right, so let's get started. Thanks everyone for joining us for ACI Ontario's first ever online webinar. Also, thank you all for making this a sold out event with over 100 participants. I guess we could say that mass concrete is quite the hot topic. We'll be recording this, so if anyone is missing out, feel free to share the link with them afterwards. My name is Stacia Van Zetten. I'm one of the directors of the chapter, and I'm going to be facilitating the session this afternoon. We're not sure yet what our new normal will be moving forward regarding our future meetings and events. However, we hope to continue this momentum, seeing more and more of you supporting your ACI Ontario chapter. Something new to report, we now have a LinkedIn group, so keep an eye out for further postings on upcoming events and just general industry discussions there. For those of you that have been attending our meetings, I'm sad that we're not going to be meeting out on the green today at our annual golf tournament. Though with the snow yesterday up here, it might be for the best. We will hopefully still be holding an AGM, however, it's most likely going to be in the fall. What better time to toss an axe or two around? Stay tuned for more information on that. A couple more things. We're looking for new board member candidates. So if anyone would like to put their name forward or someone else that you think has a lot to contribute to the chapter, feel free to email any of the current board members. You can find our contact information on our website. And then just a few housekeeping items before we do get started. This is going to be approximately a 60-minute webinar. We're going to have questions and answers at the end. All participants are muted, and you're going to remain that way through the whole webinar. If you do have a question, please use the GoToWebinar questions pane on the right side of your screen. We're going to address all of the questions at the end. As mentioned, this webinar is going to be recorded, and we'll post a link to it on our chapter website after this. So I'm going to turn it over to Oscar now. Oscar Antimate is the Chief Concrete Engineer and Engineering Manager that leads the materials engineering team in Kiewit. He has over 19 years of experience in the industry with focus on concrete materials and construction, including supporting over 100 projects requiring thermal control for mass concrete in North America. Oscar serves on several committees in ACI, ASTM, and CSA. I would list them all off, but we wouldn't have much time left for the presentation then. An important thing to note, though, is that Oscar is the chair of CSA Clause 8 subcommittee on concrete with special performance and material requirements, and recently led the development of the requirements and guidance for mass concrete published in CSA 823.1 2019. So Oscar, I think you can take control of the screen.
Perfect. So let me see. You're sharing? Okay, perfect. Show my screen. Let me know if you can see it, Stacia, so I can put it in presenting mode.
Yep.
Let me know, can you see it? Can you see it now, Stacia?
Yep,
perfect. Well, thank you very much, Stacia, and the chapter. I'm always excited to work with our Canadian partners, and sad not to be there in person. Love visiting Canada, and always a good way to share our different experiences all across North America. And I'm sad that I cannot be there in person. But thank you very much. This is an exciting topic. It has been an exciting topic for many different organizations, and CSA is one that we have been leading our efforts recently. Like Stacia said, I led the revision of the most recent publication for 823.1 published in 2019, and that's the main focus of this presentation. I'm going to be talking about some basic standard practices and performance and all that, but the focus is going to be 823.1, the 19 version. So the way that I selected to split this presentation is talking about a few fundamentals, so we kind of start setting our mindset of these discussions and why it's so important. Talking a little bit about concrete mixtures, and then go directly into the temperature limits, thermal control, and implementation. So the first thing to understand, and this is really important because there's always going to be different views and interests within our projects. there's always going to be the opinion from the client, from the owner, what the owner wants to build, why they're so concerned about things that we most likely from the engineering side or construction side are not concerned. Why do they want to achieve that? That's extremely important for all the parties to understand. Also of importance is to understand what the architect and designer wants to design for and how they're going to meet the design intent for the owner goals, for the owner vision. That's obviously going to be impacting a lot how the contractor then is going to be using information to build the project. Without having the vision of the owner, the requirements from the architect and designer, it's going to be really difficult for then the construction team to make a determination what's going to be the final goals of the project to build the project. And then obviously without forgetting what is important for the concrete materials, how the concrete producer is going to be part of all this effort and what they need to do to ensure that there's the construction demands are addressed for the construction team to build the project, and how they're obviously going to meet the design criteria to comply with the engineering aspects of the work. Extremely important. Also thinking about, okay, give me a second. I need to make some edits here. Stacia, you tell me that you're seeing the my display on the computer?
Yeah, I see the next slide.
Okay, so thank you for being,
yeah.
Perfect. So I'm gonna do something here.
That's what happened to me too.
Okay, no worries. I'm gonna be doing something then different here. I apologize.
No worries.
I'm gonna make. Let's see if this one works now.
That's perfect.
Better. Okay, perfect. Thank you very much for letting me know. So then the other thing that is important to understand as we are working on developing expectations is to understand that there's going to be intended goals from the specifications, but we need to make sure that those intended goals from the specification are clearly defined in the specs. And this is an example I like to show because you can see that in this example, there's intended goals as part of the specification, but there's no clear expectations on how you're going to meet those goals. And that's extremely important for thermal control and mass concrete too. In this case, you can see here a very broad sentence from a spec that talks about that the concrete shall submit combination of materials that produce concrete to meet requirements with respect to workability, dimension stability, freedom of cracking, low temperature rise, adequate strength, durability, and low permeability. But in this spec, and I don't want to, obviously get too much into where this project come from, what is the client that shared this spec. But in this spec, they didn't have any requirement for shrink, have any requirement for temperature rise. There was no requirement for permeability, and the only requirements were mainly, from a slump perspective and a strength perspective, and some other prescriptive requirements that were associated to the material requirements. That doesn't help much to define expectations. So it's extremely important that the specs provide clear expectations associated to the goals of the work. And another thing that in today's market we need to be aware is that in today's market, it's not only about a slump, it's not only about strength. We need to understand that in today's market, concrete is more than just a slump and strength. There's a lot of effort into understanding the performance of the work, the quality of the work, how we can achieve durability. In many cases that we have architectural enhancements, how the visual appearance of the work is going to show up, and also what is going to be the quality efforts and how we're going to meet the design and construction demands. So when we look at defining expectations, we need to understand that there's more than just a couple things. We need to put in place what is intended to be achieved with the work and how we're going to be able to have a constructible design, a sound design that is going to be able to be built in the field. So let's talk about fundamentals. And from fundamentals, I'm starting now to show some of the things that we're doing now in CSA. So one of the things that we did in CSA during this past cycle was going over everything associated to mass concrete. I'm going to start talking about the definition. You're going to see in the notes to the definition that there's a guidance provided in an annex. Annex T is an annex that allows for you to read through what is the general considerations for defining mass concrete, for implementing thermal control plans. All of that is going to be included in Annex T. Section 7.6.3 is now the mass concrete section, and you're going to be able to see through this presentation that is very comprehensive. It's going to talk about definition, about concrete mixes, about temperature limits, thermal control planning, temperature monitoring. So let's start with the definition. And I'm showing here in the screen the definition that we provided now in the 2019 version. What is important about this definition? Well, what is important about this definition that we're providing now is that it's broader into what can be mass concrete, what is not mass concrete. There's not a true one single point of dimension that is going to be able to control what is mass concrete. In general terms, there's typically a minimum dimension that is somewhere around 1 meter that you start seeing then the concrete behave as mass concrete. Is it true that if you have 1 meter, automatically you're mass concrete? Is it true that if you are at 2 meters, you're going to be in mass concrete? It depends. There's never one single number that is going to be able to define what is mass concrete. And that's going to be determined by the concrete mix you're using, by the restraints that you have in the placement, by the amount of the amount of considerations that you have for cracking control. It can also be affected by the environment. So there's a lot of different things that the engineers and the construction team need to consider for them to determine what is going to be mass concrete and what is not. It will be preferred that the drawings and the specifications identify a clear understanding for the project of what's going to be mass concrete. But from a standards perspective, we cannot establish one thing or the other. We can at least provide the definition and then provide guidance within the document to make a determination. Why is that? Why obviously is that important? As I mentioned, well, there's different types of mass concrete. And in Canada, there's you can see a lot of the traditional mass concrete in the projects like hydro projects, where you have spillways, where you have big dams, where you have some large generation of power with water in the hydro agencies. A lot of those become more of the traditional mass concrete. You implement traditional concepts of mass concrete. But also a large part of the industry in North America is the thermally controlled concrete, where you get more into the high-rise buildings, into the bridges, where you have heavily reinforced concrete, higher strength requirements, higher early strength requirements, and those are also different to the traditional mass concrete. So when you're looking at the thermal control planning, when you're looking at how you're going to implement best practices, you need to understand what are the goals of the projects. What are the type of sequences of construction operations that you're going to get in place? What are going to be the concerns from a design criteria to achieve the work, and then obviously be able to identify what thermal control practices are appropriate for the different applications. In simple terms, when we talk in ACI and CSA, this is very common. You're mainly looking at, okay, is the concrete hot enough, right? Do you have enough amount of cementitious material that are going to generate a lot of heat? Or is the dimension of the placement large enough? So what happens there? You're going to have thermal risk are going to increase as your mix have higher cementitious materials, because it's going to generate what? Higher temperature. Then also you're going to have larger structures are going to have higher risk of thermal control requirements, because what? They're going to trap the heat. They're going to show typically a higher temperature rise too. And then you're going to have to make sure that you protect the concrete from the thermal conditions. So in general terms, when you look at CSA and ACI, the main focus is going to be more into the mixes and into the placements. That's the way that we're going to try to make determination here of how to define mass concrete. Every project is going to be different. Every project is going to have a different way of looking at it. But from a standards perspective, those are the main things that you're going to be thinking about when defining mass concrete. So from a concrete mixture perspective, we also need to understand the basics of concrete mixture proportioning and what the standards typically require. There's going to be strength requirements, durability requirements, workability requirements. There's going to be aspects of economics associated to how we determine the mix proportion. But in our case for mass concrete, we're going to have also a thermal aspect associated to developing the mixes. Meaning that when you have a 35 MPa concrete mix that you're going to be using for a non-mass concrete, most likely you're going to have considerations to achieve strength, durability, workability, and economics in a different way than when you're going to do a 35 MPa mass concrete. And it's going to have to be considered. You cannot say that a 35 MPa non-mass concrete is going to be the same mix that you're going to use for a 35 MPa mass concrete. You can use them if you have them optimized correctly, but you need to understand that they're likely not going to be the same mix. And how we achieve mix optimization. And I know in Canada, there's different markets, there's different requirements of how this information is documented for different concrete mix proportions. But in general, there's going to be an impact into how you optimize the grading, how you come up with the mix proportions and ensure that there's a low water demand in your mix by improving the way you select the materials and you select the proportions. But also there's going to be an admixture enhancement for the performance of the product. So you're likely going to have to then consider, how can I reduce the total cementitious of this mix by improving the way that I come up with the aggregate combinations, with the aggregate selection, with the quality of the materials that I'm going to be using. But also then, after you do that and you have a good mix, how are you going to be improving the performance of the mix to allow for admixtures to be used in the right way. You don't want to be using admixtures as a way to solve a problem that you should have resolved with the materials from a selection and proportion perspective. You want to first have a good mix and obviously then enhance the performance with admixtures. So let's talk about temperature limits. I believe this is going to be the bulk of our conversation here. One of the biggest changes you're going to see in CSA, where we expanded how we specify temperature limits for mass concrete. The temperature requirements for mass concrete are going to be under section 7.6.3.2, and this is a very important clause here. And I want to make sure that we just don't jump into the sections below this. We want to understand what this means to the projects. The temperature requirements for mass concrete placement shall comply with clauses 7.6.3.2.2 to 7.6.3.2.5, unless otherwise specified or approved by the owner. And this is what we're doing here. We're providing all these requirements, but also allowing at the end to be the engineering team, the owner team, the project to make a determination what is going to be applicable and what is not going to be applicable. And that is an extremely important aspect of specifying. Why? Because there's no one size fits all. And if you try to establish only one size fits all for all mass concrete, you're likely going to have 50% of the times good, and 50% of the times it's not going to be very good. So with this, we have a standard that has the provisions to meet the objectives and the intent of the standard and be compliant. But we also have allowance for the projects to determine what is appropriate and what is not for different applications, okay? That allows for better flexibility and improve the performance of products. The first thing we're going to talk, adiabatic temperature rise. And you're going to think about adiabatic temperature rise in a way that how can we better manage the selection of concrete mix proportions and the selection of mixes for mass concrete. That's the main intent of this provision. And in this provision, 7.6.3.2.2, the requirement is that there needs to be an assessment of the adiabatic temperature rise, and that it needs to be reported within the mix design submittal. We understand that we're not intended here to show the mixed proportions. We have no interest of showing the mixed proportions. That's going to be something that is going to be maintained proprietary of the concrete producer, and the standard does not go into mixture proportions. However, there's a performance aspect of the mix, and there needs to be some level of calculation or testing or verification of what is going to be the predicted adiabatic temperature rise of that concrete mix. And that's all that is intended to be shown in the concrete mix submittal. So there's going to be adiabatic temperature rise considerations provided in the Annex D. Annex D is going to provide a lot of the guidance into how to select the different test methods or analytical methods for the concrete producers to evaluate the adiabatic temperature rise of the concrete. This is extremely important. And this is extremely important because without adiabatic temperature rise, to determine an adequate thermal control plan. There's no way for you to determine a thermal control plan that is going to be specific to a placement and ensuring the construction team to meet the temperature limits if there's no way to understand what is the temperature rise of the material. So this is an extremely important aspect, and is a very, I would say, interesting requirement that is going to have a lot of questions, I believe, and it's going to have to go through a good level of trial and error and practicing and verification for each of the concrete producers to get familiar. No, it's not a simple thing to just go and say, I know what it is. You're going to have to go through the annex, and the annex is going to go from the simple approach to a more complex approach. So there's a way of doing it for all the different ways that you want to implement here. So like I mentioned, adiabatic temperature rise is going to be mainly affected by the cementitious materials, the composition, the amount. More cement, obviously, it's going to cause the material to generate higher heat. Use of Class A fly ash, in the case of Ontario, is not available, but in the case of a slag, it's available. So you can use a slag, and you can use low heat cementitious materials to compensate for the heat that you need to meet in thermal control plants for mass concrete. So make sure that you understand temperature rise. In the case of adiabatic temperature rise, I want to obviously share with you some general considerations. In traditional mass concrete, you typically see mixes that have less than 45 degrees Celsius temperature rise. In thermally controlled concrete, more structural, heavily reinforced applications, you typically see hotter mixes. That's expected. You have thermally controlled concrete, typically have higher strength than traditional mass concrete. Elements tend to be smaller in most cases, and then you have more access also to different thermal control measures for thermally controlled concrete when you compare that to traditional mass concrete in dams. So that's something that maybe is more for guidance, and I'm sharing here in my presentation. So as you're evaluating the mixes, if you see a mix that you're going to use in traditional mass concrete that have too much heat, most likely you want to start looking at what to do, because it's not necessarily the best thing you can do for a traditional mass concrete placement. You want to optimize that mix. Reducing temperature rise means reducing total cementitious, using less Portland cement and using more of the class, the fly ash and slags or low heat cementitious materials. This is one example here from, concepts that are shared in the annex. You can pretty much implement computer modeling, simplified approach with the calculation that I'm going to show in the next slide. Semi-adiabatic testing, go through a full adiabatic testing method, use field placements and monitor those field placements with sensors and put insulation, and even use other methods approved by ACI, such as the Smith method or other approved methods by the owner. So in general terms, there's a lot of ways you can determine adiabatic temperature rise. It's not going to be a slam dunk. It's not going to be a single unit of measurement that you're going to be able to determine and never go and revise and verify. I always say develop adiabatic temperature rise, and then go and verify what the temperature rise in the field is compared to what you estimated in your thermal control plan, and then start working on your revisions and updates. So you better go and qualify and refine those temperature conditions in the field more appropriately with the performance of the concrete in service. So those are things that you need to understand as you implement that. The simplified approach is one of is obviously the simple method in the whole process of determining adiabatic temperature rise. It's intended to be a ballpark rough measurement of adiabatic temperature. It's not intended to be equivalent to saying we're going to determine this and it's going to be a perfect method that we're going to be used through the project. It's typically intended to be when you don't have any other way of doing it and you need to develop a thermal control plan, this is better than nothing. It's going to give you a pretty good estimate of how much is the potential temperature rise of the mix. You're going to be able to determine measures to control temperature rise in concrete, to control maximum temperatures, to monitor and control temperature differentials. And as you get data from the field, you're going to be able to revise then your thermal control plan with those revisions. This is provided in Annex D within CSA 23.1.19. Here I'm showing you the example of a semi-adiabatic testing. This is the one that we typically do the most in major projects. Myself and many other field practitioners are using this type of methods because this method actually verify the temperature rise of the concrete. So you have a 1 cubic meter into a super insulated box. You instrument the box with sensors. You leave it there for about 2 weeks, 10 days to 14 days. And all the generation of heat that occurs in that block is going to be able to then be used in your thermal model to then qualify what is the potential full adiabatic temperature rise. So it's a pretty good and accurate way of assessing adiabatic temperature rise, but this is semi-adiabatic, and you need to obviously take that information from semi-adiabatic to full adiabatic in computer models. Here is an example of using that information for a computer model where you have the semi-adiabatic test data in the left, and then you take computer modeling, and then you're able to determine the blue full adiabatic calculated curve, which is intended to show then what is the maximum potential of the heat to generate heat. That's the intent of all this, and that's the information you're going to use in your thermal control plan, and then you're going to associate that as your input to determining what are the thermal properties of the mix and how that mix behave in different placements. So if you have a understanding of the semi-adiabatic, and then you analyze the placement with the computer model, then you're able to determine a full adiabatic temperature rise, and that is going to get you a more accurate representation of the temperature rise. Then we go to temperature requirements, and the temperature requirements in this case for maximum placing concrete temperatures. So what we did in the CSA 2019 version, we look at the maximum placing concrete temperature and how does that relate to mass concrete and thermal control planning. If we have a thermal control plan, the thermal control plan is going to be able to assess the temperature rise, to assess the risk of exceeding temperature limits and temperature differentials, and then it's going to be able to determine what is the most appropriate placing temperature that you should have for your mass concrete. In many places where you are most likely in the summer, sometimes having the default limits provided by CSA are not necessarily practical. So in this case, if you have a thermal control plan, you're going to be able to justify the reasonable placing temperatures that you should have for mass concrete. So what we decided to do is put in the specs, in the standard, in the absence of a thermal control plan. So if you don't have a thermal control plan, the maximum placing concrete temperature for mass concrete shall comply with table 14. But that doesn't control plan, then you can make a determination that instead of saying that you have a 20 degrees Celsius maximum placing temperatures, you can have a 23 degree in temperature because you have just a control plan that the temperature limits provided by the specs. To allow for compliance, but also allow for thermal control plan, and based on your analysis and based on your verification and ensuring you're not exceeded, you can manage that placing temperature so you have more flexibility. The main concerns for placing temperature typically exist from, the potential effects, detrimental effects to fresh properties. Let's say that you have obviously air and train mixers, and you're going to have to pump the mix, and you're going to create friction, and you're likely going to have slump losses and air losses. That's a of discussion when you're talking about maximum placing temperatures. Thermal and shrinkage likely going to be affected depending on the placing temperature. In the actual placement, what are going to be the limits from a shrinkage perspective, the risk from cracking perspective. All of those things are going to be impacted by the placing temperatures, and also the ultimate strength and long-term durability. In the case of ultimate strength, you know that if you have a very hot mix and you allow that to happen at early age, you're likely not going to achieve the maximum ultimate strength that you want at later age. So there could be some impacts into that. And from a long-term durability perspective, there's impacts if you have a mass placement that gets extremely hot. You'll likely want to go and manage the placing temperatures because otherwise you're going to affect the long-term durability of that placement. So there's different there, but the goal of the standard is to provide the way of you should consider thermal control for you to determine the placing temperatures. Industry limits, when you look at ACI, we have up to 35 degrees Celsius maximum, and the minimum temperatures typically are in the range of 5 to 10, depending on the placement attributes. So there's room there for improvement, but do not go beyond table 14 unless you have a thermal control plan. That's the main intent. Follow a thermal control plan before you determine what adjustments you want to do. The next one is going to be maximum concrete temperature. On the maximum concrete temperatures, we had a lot of good discussions, I believe, during the past few years on what was going to be the most reasonable way of addressing this. Actually, there was no maximum concrete temperature limit in the CSA document. There was only a limit for high strength, where you would limit to 70 degrees Celsius, but there was no limits for mass concrete maximum temperatures. What we did in this case is, in consideration that we're not going to be able to have all the specifics of the concrete mix proportions, but we know that the mix design submittals are going to contain or identify their high volume SEMs1s, high volume SEMs2. That's information that is known. There's no intent here to provide to the user any of the proprietary information from the mix proportions by the concrete producer. So what we did is, in consideration of the benefits of high volume SEMs, we allow increasing the maximum temperature for mass concrete if you go to HVSM2 or HVSM1. HVSM2 is going to allow you to go up to 75 degrees Celsius. HVSM1 is going to allow you to go to 85 degrees Celsius, meaning that at that point you have, in many cases, 50% of your cementitious material are already accounted for SEMs, right? So in that case, you have an improvement in the chemistry of hydration. You obviously are already taking care of the chemistry of the cementitious materials, and given the research and the feedback from the academics within the committee, with all the research being done to date, it was found, and including ACI considerations, it was found that these numbers were going to be reasonable for the standard. This is one of those topics that had a lot of good discussions, but we provided a safe, reasonable approach to this, and we're going to keep an eye on this one during this cycle and make sure that we update the industry. We update the standard as the industry updates. This doesn't mean that if you're an owner, if you're a designer, and you want to specify 70 degrees Celsius for HVSMs, you cannot do it. Like I mentioned in my previous slides, these temperature limits are the standards, but the owner, the design team, can approve different limits. So if you have a HVSM1 and you believe that you want to go with 70 degrees Celsius, there's still, that's still under you. You own it. So there's no reason for saying that we are forced to go into this number. We have the allowance, we can do it, but the projects are going to be able to determine what is the right number for them. The main concern for peak temperatures, maximum temperatures, as many people would know, it's mainly on the long-term effect on strength and durability. On the strength, it's pretty simple. If you go to higher temperatures, you're likely going to start affecting the quality of that hydration. You're going to start affecting the chemistry within the hydration products, and not necessarily getting the best out of your concrete mix. That has been found to be above 85 degrees Celsius. The same with durability, but in durability, you have different limits. Above 70 degrees Celsius, without any mitigation, without any improvements in the chemistry, without any SEMs, for lack of a better term, you are likely going to see risk on impacting the durability of the concrete. However, as shown in the ACI documents of 308 and 201, and lots of research already completed to date, as you start providing mitigation into the chemistry, into the cementitious materials, bringing up all those SEMs into the mix, then the improvement into durability start to occur, and then you can go up to 85 degrees Celsius. There's no recommendation provided right now by the industry or consensus to allow higher than 85 degrees Celsius, regardless of the mix that you have. So the gray zone is pretty much between 70 and 85, and it's well known of the effects of SEMs, and that's why the efforts that CSA have done is to concentrate on the improvement on higher temperatures with SEMs. That's it, keeping it simple. Here is an example of the similar approach provided by ACI 201, 308. I'm highlighting the areas here where they're talking about the SEMs. Pretty much in the case of ACI, they have established more specific numbers for each of the materials. We cannot do that into the Canadian markets because there's some proprietary considerations into the mixes. So that's why now I decided to go with the classification, HVSM1, HVSM2, and then allow for that increase in temperatures as you go up in your SEMs. The next one is also interesting. We have numerous conversations on this one, and this is the temperature differential, maximum temperature differential. Many standards, including the CSA standard, had concentrated their efforts on establishing a one-size-fits-all 20 degrees Celsius. That comes from pretty much empirical assessment over 100 years ago in Europe, where they pretty much trying to figure out how can I control the concrete from having thermal cracks if if I don't know what else I can do for this material, right? Without getting too complicated. What can I do? And they found with those tests with their materials in Europe that for that application they needed to maintain the temperature differential less than 20 degrees Celsius. Now that continued to disseminate across the industry, and everybody assumed that as long as you don't exceed 20 degrees Celsius, then you don't have a problem for thermal cracking, right? Regardless of the mix, regardless of the properties of the materials, regardless of the restraints, they pretty much use that number as a one-size-fits-all. Well, that's not necessarily accurate, that's not necessarily representative, and that's not necessarily allowing the industry to improve on their performance approach. So we have now different considerations that I'm going to be explaining here, and you're going to be obviously seeing that in the CSA standard. So the first one is the 7.63251. That one pretty much goes and use that 20 degrees Celsius fixed limit as the temperature differential, okay? So it pretty much establishes the same that we have been using to date. So you go and you say that you're going to have 20 degree maximum differentials, and that's your specification. That's all you want to do. However, the standard allows you to go into other ways of specifying temperature differential. In the 7.6.3.2.5.2 allows to have a 25 degree Celsius temperature differential if you can verify that the concrete thermal expansion is less than 10 millions per degree Celsius. Why? That's well recognized. The lower the coefficient of thermal expansion of your concrete, the more resistant to temperature differentials you're going to have. And it's well reported that as you get below 10, you can tolerate 20 degrees Celsius as a reasonable temperature differential within your concrete. The other one, under 7.6.3.2.5.3, pretty much is taking a concept of how concrete behaves, right? Concrete does not start from the first day and is already ready to tolerate the same thing as it can tolerate at 7 days. So how concrete behaves? Where concrete develop properties, and then the resistance to thermal cracking increases as the properties develop. So the same approach in this case, and there's some agencies using it in North America and US and Canada, where they have an incremental approach. So in that case, and I'll show you an example, in that case, what you're doing is pretty much saying, okay, during the first 1 or 2 days, you're gonna have this differential, and then after 1 or 2 days, you're gonna have this other differential, and after 5 or 7 days, you're gonna go ahead and use this higher differential. From a smaller differential, that's the way concrete behaves. Concrete develops strength and go from the lower strength to a higher strength, and then obviously you can use that information for purpose of making your decisions. Then the last one that we have is then a full-blown performance approach. And I call it full-blown because in that case, you're truly assessing the properties of the concrete and the conditions and attributes of your placement and making a determination about what is the right temperature differential I'm going to have in my concrete work, and I'm going to do testing, and I can then allow appropriate properties. So in that case, based approach based on numerical model analysis, specific project shall be maximum concrete temperature difference limit higher than 25 degrees Celsius is permitted. So if you want to go above 25 degrees Celsius temperature difference limits, the standard tells you that you need to go through analysis and testing with the performance-based approach. And it sounds complicated, And I'll tell you this is the way that we have been doing mass concrete thermal control plants for 15 years. Just because the standards, it doesn't mean that is the industry has been establishing this performance based 15 years in different major projects accessible to pretty much all the industry. By doing this series, we are opening the door to use the knowledge of the industry and the knowledge in practice to establish standards. So this is one of is going to help a lot understand how we manage thermal control in the industry. Important, pretty much like I mentioned, cracking, temperature differentials. When you have large temperature differences, important aspect of temperature difference. It's not temperature difference, but when you're talking about, important to know that you lose heat. To understand that your surfaces need to lose heat. You don't want to be trapped by heat of hydration and leaving them inside of that insulation and trapping it, because eventually what that's going to cause is that's going to cause pretty much a longer time for you to manage those temperatures as they're going to be released into normalizing with the environment, and you pretty much are not going to be able to build a lot of work. So you need to make sure that you establish a gradual heat loss from the surfaces. That's a key element. You want to allow temperature difference to occur, but you need to create a gradual heat loss, and that gradual heat loss needs to obviously take in consideration. So that's important to understand. Now then, if we create a large temperature surface, and the tension on the surface is going to lead to cracking. So what are the things, in simple terms, what are we saying with the temperature differentials of the CSA standard? Celsius, coarse aggregate, any type of concrete, coarse aggregate, because typically when you start seeing the coefficient of thermal expansion going, when you get into limestone coarse aggregate, you're going to do testing and you're going to find likely that you're below the 10 millionths per degree Celsius for the coefficient of thermal expansion. That's very big amount. Temperature limit, I showed it there on the left side, talking about you can go from 20 to 25 in 7 days and allow that to happen. It's going to improve the way you're doing thermal insulation at a later age. And on the right side, we have there the conceptual graph for a performance based. The curve compressive strength in the x-axis and axis. And by doing that, you can monitor the development of strength in the field and then be able to assess what is the appropriate temperature differential for your concrete placement in the field and be able to then determine the thermal control measures to control those temperature differentials. You have a live basis approach into that, controlling the temperature differentials in the field. So thermal control plan, we go then down to what is important here. We have a couple of things on thermal control plan. We have the temperature monitoring, and temperature, a very important aspect of thermal control plans. And we obviously need to be temperatures of our concrete. We measuring concrete temperatures at the locations that are thermal control, and those are going to vary on the projects, on the placements, on the work. But typically, you're going to have what on the maximum core. You know, where you're in your core, where the maximum temperature is going to occur, you're going to have also going to have sensors on the outside. And the outside meaning on the rebar that is closer to the surface. Closer to sensors are going to have to be secured. Point that the standard allows to have it between 25 and 75 milliliters. Because at that location, your rebar, at that location is where you're going to If you have a point of installing the sensors that is not a place that you can secure the sensors, there's not a true way to qualify what is the measurement that you're taking and what it means to the placement. That's a very important aspect for establishing surface. Also, another thing that we put here in the notes is that in many cases we see the required corner type of sensors more for cold weather protection. They do not of the structure. They do consent of a thermal control plan. It's going to want to consider what are the major the temperature is moving and why. On edge, those are isolated locations that are mostly important for cold weather protection. They're not necessarily of interest for mostly of the mass concrete thermal control planning. Mass concrete thermal control planning wants to have surfaces that are representative of the structure, not that are just going to be driving into misplacement and then control plan. The other aspect of thermal control plans is 3.4, and that one is pretty comprehensive. It's aligned perfectly with a lot of the work we're doing in ACI. Contractors shall submit to the control plan to demonstrate the requirements. Monitoring temperatures will be achieved during the thermal control, otherwise approved or specified by the owner. Meaning that if the owner modifications to the thermal control plan, if don't need to provide a thermal control plan, wants to make different considerations to a specific, they're always open to go and adjust those for the project. But here you can see in the thermal control plan all the things that you want to consider, from the dimensions to the mix of metal to the analysis that you did, the properties of the concrete, temperature rise of the concrete, the limits that you're going to be abiding for developing your thermal controls. You can see also here requirements to avoid thermal shock. In previous versions of CSA, we have used the temperature drop. That table 20 was developed originally in Canada for cold weather concreting. It's intended mainly for removing insulation in cold weather. We decided in this case to have it just provide as guidance in the notes. It's not a requirement to comply with that, and the requirement is pretty much to have a thermal control plan that is going to specify what is the appropriate temperature drop in 24 hours. So that means that you can have, depending on the approach that you take for temperature differentials, you can have a different approach to how you manage thermal shocks, because you're going to have different properties of the concrete placement and different conditions that are going to allow you making that determination. So that's extremely important. And the criteria to terminate thermal control plan, that's also different. And when you go, you're going to find different ways that you can require to terminate thermal controls. One of the main considerations is obviously going to be, because thermal control plans are likely going to be removed after 7 days, maybe 10 days. Typically that doesn't happen that quick, as 3 days, unless you have some type of an active post-cooling system like cooling pipes. But if you get into determining what is the right approach to terminate thermal control plans, thermal control measures, then you need to allow the thermal control plan to establish that. So all of that is part of the thermal control plan that you need to include per CSA. So something to understand, thermal control plans are nothing other than a tool for the contractor to manage, to plan, to execute placements. It can help you control and monitor temperatures, reduce thermal shrinkage, minimize thermal cracks. We need to understand that thermal control plans, as I mentioned here, are intended to control, monitor, reduce, and minimize risk. That's pretty much what it is. The thermal control plan is not intended to eliminate anything. It's not intended to eliminate cracks. Well, you know what? Cracks are likely going to happen for many other reasons. Just because you get a crack in a mass concrete placement, it doesn't mean that you do not have a good thermal control plan. Most likely that's something that needs to be discussed with the design allowance for cracks. And many, even the reinforced concrete elements that we see in these days, many times have huge amount of restraints that are not allowing, for having a no crack situation. So that's very important, because many people get excited when they see cracks, but they need to understand where the cracks come from. The structural design most likely already allows for cracks. The thermal control plan did everything they could to manage the cracks. But what is the crack tolerance in the projects, and what is reasonable to obviously make sure that you can build a project within the scope. It's going to allow you to understand the behavior of the mixes, the placing cycles, maximum temperature differentials, compliance to temperature conditions. Duration of thermal control is extremely important for thermal control planning. You need to understand how long is going to be the thermal control in place, so you can determine also how you're going to cycle and schedule your job, and corrective measures. Many times you get into situations that you have to put cooling pipes. And that's part of evaluating a thermal control plan. You may have to evaluate putting liquid nitrogen or having to do a major change in the mix. All of that is going to be something that you're going to be able to determine by looking at the thermal control plan. So the last part of my presentation, which is implementation, pretty much going to go over the basic steps, right? Now that we know the standard, now that we know the requirements that we have in CSA, what are the basis of all this work and how we can achieve it in practice, right? So the first thing, analytical modeling, we need to make sure we do some type of assessment, evaluate it, model the system. Then we develop a thermal control plan with all that information, right? Field implementation. After you have a thermal control plan, you need to verify that you have a way to implement it and that you have a plan that is going to be achievable in the field. Once that plan is in place and you execute the work, you need to do what? Verify and validate that the plan that you had is working. What happened then? After you verify and validate, you go and do what? If there's a revision and update needed, then you go and do a revision and update. And why this is important? This concept is extremely important because thermal controls are to some extent live documents. You maintain to observe and monitor the generation of heat in the field, and because the weather conditions and the construction conditions are not perfect, you're going to have to then make adjustments. So you need to have a process. It's about having a process to generating a thermal control plan and implementing it correctly. It's not going to be a one-size-fits-all forever. So here are some examples. You're going to go and do analytical modeling, right? This is an example here. You're going to see what? The amount of generation of heat. You're going to see the generation of heat at different points of the curve. You're going to see that if you need to do cooling pipes, how can you implement cooling pipes? All of those conditions are going to be part of our analytical model. What about then how you produce a thermal control plan? What are the considerations for the user? What the construction team is going to want to know? Well, here's an example of a more comprehensive table that we have, and we use these type of concepts where we pretty much have a full year-long assessment for different weather conditions and different installation conditions. You can see that you can identify the ambient temperature conditions, what's going to be the different placing temperatures that you can consider in your decision-making process. And then in this case, do you want to have insulation? What type of insulation you can use to comply? I'm just showing here some examples. And in this case, if you go with a light insulation and your ambient temperature is 50 degrees Fahrenheit and 70 degrees Fahrenheit, and you use R1 insulation or light insulation, you know that you're not going to be compliant to the 35-degree limit. However, if you go and place the concrete at 60 degrees in this case, or if you decide to use insulation that is thicker, you're likely going to be able then to determine that the thermal control plan is compliant for your placement operations. So that's a way to look at a table like this. In this case, we also, is of importance, and I'll show you why, it's of importance that then we have the termination of thermal control plan is based on a 50-degree Fahrenheit temperature difference between the ambient and the core, and that's equivalent to a 25-degree Celsius temperature difference between the ambient and the core. Why is that? Because you know that when you're going to remove that, it's already 7 days later, and after 7 days, your concrete is already going to be able to tolerate the 50 degrees Celsius. That's something that the thermal control plan is going to be able to determine as you run analysis and you understand the properties of the mix. In this case, I wanted to show here an example, and I have it in English units, it's not metric units, but the 25 degrees Celsius is 50 degrees Fahrenheit, 20 degrees Celsius is 35 degrees Fahrenheit in temperature differentials. So you see the impacts from making a decision to terminate the thermal control plans at 20 degrees or 35 degrees Fahrenheit versus having a concrete to be terminated at 50 degrees Fahrenheit or 25 degrees Celsius. That you can actually reduce the amount of thermal control, because at that time what's happening, you're allowing the concrete properties to develop during time, And at that time, you can tolerate that temperature differential. That's something the thermal control plan can allow and can evaluate on a case-by-case basis. Field implementation, as you can imagine, different ways of implement different conditions. Temperature monitoring, as I mentioned, make sure that you secure that into the rebar closest to the surface. Then obviously, if you need to have liquid nitrogen or use ice, you're gonna have to make that determination for pre-cooling. Insulation from a model compared to insulation from the field is gonna be different. And that's one of the most important parts of field implementation, that you need to verify that insulation is accurately represented in the model, but it's not gonna be perfect. Nobody can represent insulation or weathering conditions perfectly in a model. That's a complete science project, an academic exercise, but in practice, it's going to be impossible to do in that determination. And then if you need cooling pipes, you need to make that assessment too. It's part of the thermal control measures that you can consider. In many cases, that's the way to go. Many cases, you don't have to go that way. Here is an example of a verification and validation, where you can see on the right side a graph, and you can see the temperature from sensors in the field, and how we were able to go and qualify in our models the temperature that we were expecting to have, and the behavior of the temperature in the field. So you can compare how your model and how your field sensors are showing you the temperature to be gaining heat and to be losing heat. And you can then modify the parameters, and you can determine how you can most accurately represent the field with your model. It's all you're trying to do. What is the best way for me to represent the field with the model? So this is a way of doing verification and validation. And here on the revision and updates, I believe the best way to understand this is, when is a revision necessary? When do we need it? You know, do we have issues with the model being inaccurate? Do we have issues with the change of construction sequences or materials or means and methods? And then other things that we can consider, right? If we have inadequate field implementation, is very common. Many times we see the field implementation is not accurately represented, you know, as we recommended in the models. The field conditions changed. We have a cold front, and they didn't account for the cold front, or we got rain, and they allowed the rain, and they did not protect the concrete surfaces, or the formwork and the formwork and installation have some changes, and we did not account for that in the thermal control plan. Was there any field operation that affected the whole measurements? Did they install the sensors in the right locations? Did they produce the right mix or use the right mix? All of those things are going to be part of your process that you're going to use to determine if you need to do a revision or an update. So now, to be on time, pretty much the closing remarks, right? So from a knowledge and standards perspective, I think that we are in the front of this industry. CSA has adapted knowledge into their standards for 2019. That's a great thing. That's a big win for CSA. Temperature rise, you want to know it. You want to make sure you optimize the mixes to reduce heat. You want to make sure you understand how much temperature rise you got in that mix. Temperature limits, we have a maximum peak temperature. That's your Tmax. Make sure you understand mitigation and how you can mitigate the potential issues to exceed the temperature limits, and how you can justify using different cementitious materials to improve the quality of that heat of hydration. The other part is temperature differentials. How can you develop appropriate temperature differentials for your project? And how can you consider testing and analysis to implement performance approach in your projects? That's going to allow you to create a more efficient and you know, a reasonable thermal control plan for your projects too. And in general, thermal control, establish temperature monitoring, surface protection, and performance-based parameters. Those three things are going to be the key to ensure that we have adequate thermal control plans for construction and are within the reasonable approach provided in the CSA standard. So with that, thank you very much. I open now to a lot of the questions and comments I assume that we have. And I hope you enjoy the presentation.
Thanks, Oscar. I think I'll just leave this slide up. I had another thank you question slide. I might as well just leave this one up. So for those that don't know, you can type a question in on that side panel if anyone has We actually, but I have some, and I think that there might be some more coming in. I have a question about surface protection for thermal versus curing. These elements are C1 elements, so you have to leave your curing on for, let's say, 7 days. But what if your thermal control plan says that you can remove your thermal insulation? What are your experiences with that, and just like the constructability of it?
Yeah, so that's an important question, and many people mix. Curing is different than thermal protection, right? The protection for a thermal control plan is intended to control temperatures. Temperatures is part of the curing, but that doesn't mean that because you remove thermal protection, because you allow the temperatures to show up compliant, you're affecting the curing. You need to maintain certain temperature conditions. You need to make sure you're compliant from a temperature perspective, but how you manage a curing plan, how you manage a thermal control plan are completely different things. And that even comes sometimes when people ask me about, can I remove the forms? The same thing. You can remove the forms based on the specification requirements, based on strength requirements, based on the conditions of the work that allowing you to remove the forms. And then what happens is you need to reinstall the thermal protection to make sure that you continue to provide that thermal protection. Well, the same happens with curing. You can continue to provide curing without having an insulation on top of the concrete if that allows the temperature compliance to occur. And the other aspect about curing that many times come into place is, well, we have now this water curing requirement, and that water curing requirement is likely going to cause a thermal shock on the concrete, or it's going to create a condition that is going to remove a lot of the heat from the surface. Those are things that need to also be accounted for when we're protecting mass concrete for temperatures. And the annex, in this case, CSA addressed that in the annex. We provide precautionary measures for what we don't want is to start saying, oh yeah, we want to create water curing environment. Yeah, but now you're affecting the whole intent of the thermal control plan. So you want to make sure that there's a well balance of how you protect the concrete for curing, how you protect it for thermals, but they're not the same. That's a good point to make. They're not the same.
Okay. And okay, here's another one that came in. It's not for me, I promise, but how can we use technology better for thermal control, planning, and monitoring? Any good augmentation technologies out there for field or computer?
Well, yeah, so we're talking mainly about sensors, I assume in this case. Technology obviously goes beyond sensors. I'll try to keep it simple because technology, we can even talk about models. We can only talk about analysis. We can talk about testing, technology, or even chemical and mixtures technology. So I guess in this point, it's more thermal control, temperature sensors technology. The way that I see this is more into the field implementation. Of these questions about what is the best sensor, what is not, I never get into that. It's not my problem, to be honest with you. I tell you, the sensors need to be reliable. Sensors need to be strong enough for field operations and construction. They need to also be easy to use, and they need to provide. So when you think about is they need to work, they need to work, and the user needs to be able to use it correctly. Then the other part of sensors is put them in the right place. I've seen projects many times that they just want to put sensors everywhere. You know what? This is one of those cases that too much information is not necessarily better information. Putting a bunch of sensors all around are just going to drive nuts everybody. It's just going to the way you're managing thermal controls. Mass concrete thermal control planning is intended to manage thermal movements of the structure, not intended to go into the little corner that is never going to generate even any thermal movement because it doesn't have any thermal temperature rise. And then you're going to be looking at that little corner and saying, yeah, this corner never generated enough heat, and I have this side here that has a very high heat. My differential is extremely high. Yeah, you know what? That is a condition that is a unique condition for that corner. Is not generating any movement. Where you do care to implement time and spend time is putting the sensor in that case where is the heat losses mainly coming from? What are the surfaces that I need to protect the most because they're going to create the representative behavior of that mass concrete? Well, let's say a slab. If you have a big foundation slab that is 2 meters thick, where do those sensors go? Well, most likely those sensors are going to go in the rebar closer to the top surface, in the rebar closer to one of the sides, in the core of the structure, where you're going to have to secure that sensor in the very middle of that foundation slab. And those 3 points are going to be pretty much the points of measurement that you're going to be able to use to monitor what are the temperature differentials, what is your maximum temperature. And you're going to manage insulation the same way all across the board. So if you are making a decision based on that, you need to use the same insulation efforts all across the board. I can tell you I've done hundreds and hundreds and hundreds of thermal control plants that way. Mexico, Canada, and US, it works beautiful. If you complicate it with technology, technology is as good as the user. Don't try to bring technology or try to put too much technology that then is going to create confusion. So that's the part on temperature sensors.
Okay. Can you speak quickly on types of SCMs and what the max percentages you see in projects would be?
Yeah, typically, obviously we're in Ontario, so I'll concentrate my first thing on slag. I think slag is the main SCM for you there for temperature rise reductions. You guys also have low heat of hydration cement, so LA cement is available in some markets there. But from a slag perspective, up to 70 to 75% slag is what we see around in North America. I can tell you we have done 35 and 40 MPa concrete with 70% slag concrete in New York, which is very, very similar weather conditions than you have there in Ontario for the winter. And the strength, we're all over compliance at 7 days. So just because you have a high volume SCMs like a slag, slag typically has both pozzolanic cementitious properties. So it depends on the slag source, it depends on your cement source, but up to 70–75% slag is very common on mass concrete placements. There's more into it. There's more discussions, right? What is exposure conditions? What is the surface protection you're going to provide? What is going to be the level of curing? All of that comes into place. That obviously is another hour of discussion. But from a percentage perspective, for bridges, infrastructure, we have used 70–75% slag. In fly ash, you go more into the 50s. 50–55 is the most I've seen for Class F fly ash. Class C fly ash, very common to see it at 50 and even up to 60. But it's not that common to see Class C fly ash in mass concrete. Most of the specs do not want to have Class C fly ash in mass concrete. So I can tell you more into the 50s for fly ashes and up to the 70s for slag.
Okay. Another one. Do you think the max temperature requirement for mass concrete should be consistent with the max allowable temperature for accelerated heat curing?
You say for like precast operations versus mass concrete?
Referencing CSA 23.4, so precast, yeah.
Oh, yeah, correct. So we're talking about accelerated precast. Well, you know, it's all about chemistry, and the chemistries and amount of cementitious materials, supplementary cementitious materials in precast completely different to cast in place mass concrete. So it's all about what are the materials you're using. I cannot tell you that the temperatures need to be the same. Yeah, they need to be the same if they have the same materials. I don't see why we need to differentiate in this case between the accelerated heat of hydration to the same of a mass concrete heat of hydration. Actually, if you see how temperature generating some of these mixes in some of these large placements, you pretty much get that hot in the first 24–48 hours. So it depends on the regime that you have and the cooling. Now, I believe more importantly in a precast structure is how you cool it, because I believe that's going to be the main difference. And you have to cool it pretty quick compared to mass concrete. So the main differential there is cooling and cracking tolerance. If you can heat it up all the way up and cool it down within a reasonable time for a precast element and not cause excessive cracking, in that case, I don't see the need to have a problem specifying the same temperatures for purpose of durability. But you need to have the materials that are appropriate for that temperature. I cannot tell you that you're going to go with a high early strength cement without any SEMs, without looking at the chemistry, and go ahead and pump it up to 85 degrees Celsius, because that's not appropriate. But if you have a mix that have 50% slag and you want to use for precast work, and you can tolerate up to 85 degrees Celsius, I don't see a problem with that, because you have 50% slag.
Right. Okay. What's your experience with Portland limestone cements and its effects on temperature control versus just GU cement?
Right now they're showing up in every market, I can tell you. Every market is showing the PLCs, Portland limestone cements all across the board. I can tell you maybe in the last year is where we have been getting more into it. There's a lot of good research around. I cannot tell you I have done a true comparison of what the PLC is. And one of the reasons why I would never be able to tell you specifically the comparison is because I touched too many markets to give you a true comparison. I'm going to give you maybe a global comparison that everything looks about the same. But for me to compare it to you with a PLC on a certain market, it's going to have to be kind of a little bit of a little project that I do to compare that. What I've seen, very equivalent GU PLCs showing up about the same. Chemistries are slightly changing also on the pozzolans, on the slags and fly ashes. So I cannot tell you if a lot of the similarities is because also the slags and fly ashes are changing, or because it's just showing to be very similar. As much as I can say.
Awesome. I think that's it, unless Alan, did you have any more questions?
No, I'm good on this end.
Oh, wait. Oh, we just got a clarification. Okay, I think that's it. Thank you so much, Oscar, for presenting. Thank you everyone for joining as well. We're going to be keeping our members up to date on future meetings and events through email as we normally do. But as I mentioned before, we have LinkedIn now, so it would be great if everyone can join our group and just keep the conversations going on there until we can have an in-person technical meeting sometime, hopefully in the fall. So thank you guys. Thanks, Oscar.
Good, thank you very much. Thank you very much, Stacy, and the chapter. Like I said, it was a pleasure, and always enjoy spending time with you, and hope you learn something today. If not, CSA 23.1.19 version is available there for purchase, and it's a wealth of good amount of information if you want to keep reading into it. Annex T is amazing, so enjoy it.
Perfect. Thank you.
Thank you, guys.
Take care.